Hello and welcome. Interesting one. Advanced portfolio optimization using numerical optimization algorithms. In this series, we are taking a look at calculating the efficient frontier for a large number of assets, e.g. an index, in this example, the Dow Jones Industrial Average. In this one, we are focusing on building the efficient frontier, which is this blue scatter in the chart here. Based on this and potential follow-up videos, we are also taking a look at Sharpe ratio and global minimum variance optimizations, so your feedback is basically existential. Before we are starting, I recommend to have a solid understanding of calculating portfolio expected return, volatility, and modern portfolio theory in general, so I'm not going to cover it in this video. You can take my course, obviously highly recommended, or if you want to have a free option, just check the videos on my YouTube. To recap, what was our approach until now? We were considering a very limited number of assets, say 3. Then we were creating a large amount of portfolios taking random weights, ending up with an efficient frontier shape, which is just forming due to the amount of portfolios we were creating, which by the way is perfectly fine for the beginning. However, with more and more assets, this approach won't work due to computational limitations. As a side note, just try it for only a 10 asset portfolio. You will see that you will need millions of iterations to form the frontier. What I can tell you for granted is you will definitely have a hard time calculating an efficient frontier for an index or whole market. What is the solution therefore? You need to use numerical optimization algorithms, which is exactly what we are going to do. Before doing so, for better understanding of the optimization in general, let's talk about what you are actually optimizing when calculating the efficient frontier. That is, for a given level of return, you want to find the weights of the portfolio components or simply assets that minimize the portfolio risk, which is measured via the portfolio standard deviation, as you know. There are two important constraints to this optimization, which are first, sum of the portfolio weights must always equal 1, so you make sure you are 100% invested. Secondly, for each point on the efficient frontier, you need a target return. The portfolio return then, which is, as you know, is the weighted sum of the assets expected return, must match that target return. So what is the target return and how are we tackling this? We simply take the minimum as well as the maximum return of the components and create a linear space between those. Or in simpler words, we just draw a line between those 2 points, minimum return and maximum return, and go over this line with the exact same step size. Example, max return 10%, minimum return 0%. If we consider 3 target returns, you would get a linear space of 0, 5, and 10%. You will see in Python how that looks like for even more clarity. Finally, we also need bounds for the optimization, which is the weights have to be between 0 and 1, avoiding short selling or leverage. So let's switch over to Python and calculate an efficient frontier for the Dow Jones Industrial Average using numerical optimization. Alright, let's get started. As you see, we need a couple of libraries here: NumPy, Pandas, Matplotlib, yfinance, and the minimize function from SciPy for our optimization. Next, I'm going to pull all ticker symbols which are currently in the Dow Jones Industrial Average, just using Pandas convenient read HTML function for that, and provide a link to the Dow Jones site. Just copy pasting that here. So Wikipedia page, simple as that, and it's the second table, so I'm indexing for 1 here. So this is looking like this. So you see the symbol column here contains the ticker, which we can then pass to yfinance to pull price data for those symbols. So these are our assets. So let's pull price data. Just storing that in data, use yf's download function. Take as just shown symbol, provided in list format. And let's just, as an example, start in the beginning of 2021. You can start whenever you want. Just an example here. And I'm taking the adjusted close column here. So with that, I'm getting price data for all those assets. So for instance, we are getting a time series here, Apple prices from the beginning of 2021 until the last trading date here. And every asset is a column. So we have 30 columns and 800 rows here. Next, we are calculating returns. I'm just calling it as it is, returns. Use the PCT change function on the close prices to get the relative change here, not working with log returns here. Perfectly fine for this use case. And with that, we are getting a data frame containing the daily returns for all assets. Out of this data frame, we can define two important components we need, and that is the expected returns. With that, we are just taking the mean of the returns and then we are annualizing it. So we're just multiplying by the number of trading days here to get the annualized return here. Same story for the covariance matrix. So just calling that cov matrix. Use the cov function on the return data frame and also multiply with 252 trading days to annualize it. So we have the expected returns, we have the covariances. Now let's define our function which we are passing to the optimization algorithm. So as explained in the beginning, we want to minimize variance or also standard deviation, which we are taking care of later on. But for now, we are minimizing the variance and then simply square rooting it in the end. So just calling it as it is, portfolio variance. And this is taking an array of weights in it. And as you know, portfolio variance is just the dot product of the weights with the covariance matrix. And then again, the dot product with the weights, as explained in my course or in the YouTube videos in detail. So we have our function, and now let's define our number of assets. As you've seen, the number of assets are simply the number of columns in the returns data frame or also in the data frame. Doesn't matter, but I want to store it in a variable just to save myself some coding time here. So I'm just taking the length of the columns here, which is just, as you've seen, exactly 30. We have the number of assets. Now let's initialize our weights. So background here is, as you know, you have to start at some point. And what is the starting point? The starting point is equal weights. So what are equal weights? Equal weights would be every asset is weighted with 0.03, so 3.33%. Now we need that in array form, so we need an array of 0.033 with the shape of the number of assets. And there are basically tens of ways to do it. I'm just doing it very straightforward. I'm doing it like this. Just define initial weights as a numpy array of, and then simply take 1 divided by the number of assets for I in range of the number of assets. So using a list comprehension here to achieve that, and I'm getting an array, as you see, with a shape of 30 containing equal weights as my initial guess for the optimization. All right. Next up, very important, my target returns. As explained in the beginning, what is the idea? We want to get target returns. And what would be a good way to get target returns? To pull the minimum expected return and the maximum expected return. And then we want to just create an array of evenly spaced numbers. So let me give you a very straightforward example. I have, what did I say in the beginning? I think I have 3 target returns, and I have a minimum return of 0 and a maximum return of 10. That was the example. So if I'm using NumPy's linspace function now, which is creating an evenly spaced array of values, and just take my example, so minimum return was 0, maximum return was 10, and I want to have 3 target returns, I would get 0, 5, and 10. All right. If I take 4 target returns, I'm getting 0, 3.3, 6.6, 10. I think you get the point, right? So how would that look like in a graph? Yeah, NumPy arrays, you cannot plot like this, but you can do it like this, hopefully. Yeah, you can. So you just get a straight line, and you have the exact step size I showed you. All right. So this is what we will use for the target returns. Just getting an array of evenly spaced values. So in simpler words, just an array with values with the same distance to each other. So let's use that and call that target returns. And as said in the beginning, we pass the minimum expected return, so expected returns min, and the maximum expected return. So max, and then I'm just taking 50 target returns here. You can take 100. With that, you're just getting more points here, but I think 50 are sufficient for now. So we have 50 target returns. So this is just looking like this. So this is the minimum return. This is the maximum return. And as you see, evenly spaced. So same difference between the values. And now what we are simply going to do is we find, for all these level of returns, we find the minimum risk. So how are we going to do it? We are looping over this array, and then for every return, find the minimum level of risk. And then we already have the efficient frontier. So we are starting with target vols, so target volatilities, and then we are populating this empty list for target return in target returns. And now, very important, define the constraint as explained in the beginning. So first constraint, as I said, is the weights array must sum up to 1. All right. So you can do that by defining an equal type function and then provide a function. And I'm just using a lambda function for that. So lambda of whatever is the sum of whatever minus 1. And that must equal to 0. So this simply means it has to equal 0. If it doesn't equal 0, the constraint is not fulfilled. So the constraint is this term has to be 0. So this is our constraint here. This is what this means. Second constraint, as I explained, so you're just passing it as a tuple and then you define the constraint as a dictionary, as you see. Second constraint is the weighted sum of the returns has to be equal to the target return. So whatever weights you're passing, you have to get the target return with it. So same story here, so I can just copy paste here. So now we need a function, and how can we do that? We are simply taking the weights vector, take the dot product with the expected returns, and then subtract the target return. With that, you ensure that you have the target return with your weights. So lambda x dot product with the expected returns minus the target return. Then close it, as these are our constraints. And then, as said in the beginning, we also need bounds. And it's a bit inconvenient for the optimization function or the minimization function from SciPy. You need to provide the bounds for every single weight. So meaning you need to provide the bounds like this. So if you want to have bounds of 0 and 1, you could create a list of a list and then multiply it with the number of assets. And with that, you would get 30 bounds, which you actually need because you have 30 assets. So you need to provide the bounds as this is shown here. So I'm just going to do that, just defining the bounds as 0, 1 times the number of assets, as explained, just to avoid negative weights, avoid short selling, leverage, whatsoever. So we have our constraint, our bounds, not bonds, sorry, our bounds, and then we can run our optimization function. So storing that in results, use minimize, then provide the function I want to minimize, which is my portfolio variance, provide my initial guess, which is my equal weighted array. Then the method I want to use, SQP, sequential least squares programming, provide my bounds as my defined bounds, and my constraints as my constraints. With that, I would get my minimized risk here per target return. So as we have 30 target returns, we want to have 30 risks. So we are just appending to my target vaults here. So target vaults, append, and then the result of this. And the result of this, I've covered that in some of my previous videos, I think. So the result is just containing some information, but relevant for us is the fun part of it. So I'm just accessing the result of the optimization and access the fun, which is just the minimized volatility. And as this is a variance value, I'm just taking the square root out of it to get the portfolio standard deviation and store that in the target volatility. So let's summarize what this code is doing. It is looping over the target return array and then defines both our constraints. So weights have to sum up to 1, and the weights times, or the dot product of the weights with the expected return, have to be same as the target return. We don't have any short selling or leverage, and we are just minimizing for portfolio variance. And then we are appending to our target volatilities list for every given target return. So overall, we're running 30 optimizations here. So let's run this. And with that, we are getting our target volatilities, as you see here. So last but not least, we want to visualize here, and that's straightforward. So you're just pulling a scatter plot, take the volatilities on the x-axis, just taking target volts here, the target returns on the y-axis, and give that a nice label, efficient frontier for efficient frontier, and then give it a title, PLT title, efficient frontier for the Dow Jones Industrial Average. And maybe let's make it a bit more meaningful. X label is volatility, standard deviation, and the Y label is the expected return. That should be it. So let's take a look at that. And we have our efficient frontier as shown in the beginning. And that's and that's already it for this video. I hope you found this interesting as I found this. And yeah, in the next videos, we are going to take a look at optimizing the Sharpe ratio and the global minimum variance portfolio. So that's going to be extremely interesting. So thanks a lot for watching, and I'm looking forward to see you in the upcoming videos. Bye bye.